Welcome again. Uh, I'm Rasan Kumar Singh. Now let's we start our next part of presentation. Before this, just to take up our previous uh, presentation in which we just talk about the ray optics and wave optics. In previous presentation, we just saw that the theory of the light is starting with the ray optics, which is very simple theory that describe the or explain the theory of the reflection and reflection, but it's failed to explain the diffraction and interference. Then the a new theory just came in, which is wave theory, in which we see that the light travel like a wave, and also in theory of diffraction and interference, we say that there are also a phase difference of the wave, which is just generated due to their path difference. And according to their phase difference, it is treated as either coherence or incoherence. But after wave theory, in some experiment, it has been seen that when we just perform experiment, then during that experiment, researchers saw that there's some phenomenon like beam. It can be split into two or three form, and also when it transferred to the some medium, they incline to some angle, and the wave optics theory could not explain it why such phenomenon occurs. Then uh, the one scientist, which is the James Clerk Maxwell, who just perform, who just provide the theory of electromagnetic optics, in which he proposed that optics have electric as well as the magnetic field, and since both are the vector, that's why they treated the light as a vector quantity. And for this one, they proposed a mathematical equation in free space as well as the in the medium. Now let's we see. We see the in this slide that the only difference is the component of the electric and magnetic field, which is perpendicular to each other, and they also perpendicular to the propagation of the wave. And of course, this is the equation of the wave h mu, which is equal to the hc by lambda, where c the speed of light and the lambda is the wavelength. This is the difference only in with the wave optics is that wave optics treated as a scalar, but the electromagnetic wave treated as a vector with the electric and magnetic field. Maxwell just to give these four equation. The left side is the Maxwell equation in the free space, and the right side, the equation is in light propagate in the medium, where there is no free charge. Just the first equation is the Ampere's law, in which it said that when there is any change in the magnetic field, there is a generation of the time varying electric field. This is also Ampere's law. In second law, it said that when we change the electric field, then we get the time varying magnetic field. In the next to the Gauss law, which is the just a convergence of the electric and magnetic field. That's why it is zero. Another the right side equation is the Maxwell equation in the medium, in which there is no free space, free charge. That's why there are displacement current and the magnetic field, a magnetic intensity. And the displacement current is related to the magnetic field and polarization, and the magnetic intensity is related to the magnetic field and the magnetization. Epsilon is the uh, permeability, and the mu naught is permeability. In this equation, the just electric field is replaced by the displacement vector, and the magnetic field is just replaced by the magnetic flux. Now, when we just try out to find the solution of the Maxwell equation, then we get the three types of three equation, and this is the just three types of elementary electromagnetic wave. First is the plane wave, in which the E field and H field both are the perpendicular to the K vector, which is the propagation of the electric field. And follow these two equations. We see that this equation is the vector product with when two field get vector product, then we get the third vector. This just follow the vector cross product of the vector. Second is one thing is the wavefront is in a plane. All the locus of the wavefront at the same instant of time is a plane. In a spherical wave, the amplitude is the wave propagate in the radial direction, and we get the equation is 1 by r with the phase value. Phase is also changed in the radial direction. Third is the Gaussian beam, in which it is the beam travel with non-uniform field. In both plane and spherical, there is a uniform field, but in Gaussian, there is non-uniform field. The next term is what is the polarization. First, because one of the main theory behind the development of the electromagnetic wave is the polarization. Then what is the polarization? Polarization is just a direction of the electric field in which the electric field oscillates. At the fixed time, there is a fixed direction of the electric field. When this is the how we denote the electromagnetic wave with the frequency mu and the angular frequency omega, and let's just travel in the z direction. Then we denote the electromagnetic field through this equation. And electric field is a vector quantity. Then there, when we can uh, just denote it as a component of the direction. In this figure, there is some random wavefront traveling in z direction. We see that their wavefront is not uniform, but in the second, but they have some polarization because their electric field inclined to some direction. In this figure B, we see that the wavefront is in a plane. That's why it's a plane wave, and they have, at instant time they have uh, electric field at some angle, and they just travel in the z direction. There are some three types of polarization. One is the linear, uh, spherical, and the elliptical. It depend on the phase value of the electric and the magnetic field. Since the electromagnetic field has both of field, electrical and magnetic, they have also some maybe phase difference between this field. And on the basis of the phase value between the phase difference between the electric and magnetic field, their polarization also different. Suppose that there are when the phase difference between the electrical and magnetic field is either 0 or pi, then we get this equation. Then the one electric field is a linearly related to the other electric field with the red amplitude, and that's why it's in a linear form. And so that we just call it as a linear polarization. We see that when the when there are a difference pi by 2, then its component is just we get the in a linear form. It's not rotate. It's not get any uh, go through any non-linear path. It just follow a linear path. But when the phase difference is pi by 2, then it's the electric field propagate to the z direction. Then it seems to be like a rotate in the same manner. And the electric field and magnetic field, both component is treated equal, and just follow this rule. When we just get the simplify it, then we get equation similar to the circuit. That's why we call it a circular polarization. When it's rotating clockwise, then we call it right circular polarization. And when it's anti-clockwise, then we call it left circular polarization. It depends on the phase difference, either it is plus or minus pi by 2. Now we see that what happens when the phase difference is 0, pi, or plus minus pi by 2. But what happens when the phase difference is beyond this angle? At this angle, then it's travel in a helical path. When the phase difference is neither 0 nor pi nor plus minus pi by 2, then the wave propagate in a helical path. We see through this equation. When we simplify it in x in y, then we get the equation. And we keep if the phi is neither 0, pi, and pi by plus minus pi by 2, then we get as a elliptical equation as in the form of helical path. That's why the wave travel in the helical form. And that's why we call it elliptical polarization. As you remember that in the ray optics, when we have to find out the position and the location of the ray optics in the medium, then we use the transfer matrix. In this similar way, if we wave travel through the any optical medium that change the polarization, then how we get the output polarization? For this one, we again, since the polarization is a vector and we treat it as a vector, then the output polarization, just since the polarization can be expressed as the what is the vector component, then the output polarization can be expressed in terms of the input polarization. And similar to transfer matrix, we just express in the linear equation and get the matrix which is called the Jones vector matrix, which is just related to the input polarization to the output polarization. And from this matrix we can get the what is the our output to electrical or magnetic field in terms of input field. Let's some example of the matrix polarization. Suppose that our linear polarization. Linear polarization is just there is no any angular term. That's why it's come denoted as this Jones matrix 10101. Suppose that if we want to convert into some angle, when we induce the angle, then it's maybe chance that the polarization change into linear to no circular, elliptical, or circular to linear. When the material, when we that change the polarization of the light, we call it wave retarder. It's either pi by 4 wave retarder or pi by 2 wave retarder. It depends when it convert linear into circular or circular into linear, or convert into circular polarization to the right circular to left or left to right. Then we in this matrix we induce the some phase that can change the phase and just change the input polarization. Now, in this slide, we see the uh, how we can electromagnetic field theory explain the reflection and refraction of the electromagnetic wave. Suppose let's wave, electromagnetic wave interact with the boundary of the two medium, and one uh, uh, part is reflected, one part is reflected, and one is transmitted or refracted to another medium. Then we get the reflection and the transmitted matrix, which is just denote the part fraction of the uh, input wave, either reflected or transmitted. When we, if the Fermat equation, we know that the Fermat is scientist which just contribute in the field of ray optics. Using their formula, then we get the reflection coefficient and the transmission coefficient. Here we say that the incident wave, there are component is y and x. There are electric and magnetic field component in both directions. And the same that Rx, Ry, and Tx and Ty is the reflection and transmission coefficient in their term in respective direction. There is a question in which we say that how the refractive index affect the velocity of light, or their the permeability or permittivity affect the refractive index of the material. When this is the equation in the when the material is having both electrical and magnetic property, but when the magnetic property is absent, then we can just denote the refractive index of the material with the ratio of the permittivity. And again, this is the related to the susceptibility of the material, root over 1 plus psi. Here we see the property of the electromagnetic wave, how it's developed, and how to explain the polarization. But now, in after some time, there are some other property explored. Like one is the main experiment is the photoelectric effect, in which the when the photon is tagged with the material, they generate the photon. Then, but the electromagnetic wave, till now we consider wave as a continuous. Fails to explain why these types of energy come out when the photon is tagged to material, because it's a continuous, but we get the discrete form. Then the two scientists work in this field is the Max Planck and the Albert Einstein. Max Planck just quantized the nature of radiation. According to the Max Planck, the energy is quantized in the form of frequency. And the Albert Einstein just so that it's not only radiation, it's also work on the light. The light is a bundle of a small packet of energy, which is also quantized. And this two theory just develop just what is the so the path, the forward path in the field of light. And then the concept of photon comes when the Einstein just named as a light particle as a photon, which is just a having energy in discrete form. I think it's stuck. Now let's see. There are some theory of the photon. What is photon and how it's developed? We know that initially light treated as a wave, but not wave. It's also act as a particle. Then there is a theory come out which is known as a wave particle duality. So the particles can behave as a wave or as a particle. Max Planck so that the when the light emit, it's not continuous, but it's a discrete or quantized form of light, which is the in some factor of the frequency, which is the factor h is which is known as a Planck constant. And we discussed it about Einstein. So the quantization was not just inherent to the light; it's just about it's related to every radiation. And we just give a name, a photon, and that can explain the photoelectric effect later. This photon uh, carry both electromagnetic energy, which is similar to h mu, as well as the momentum. Also, the angular momentum similar to the electrons. And this proton treated as zero mass, having no mass, but can travel at the speed of light in vacuum. And with this equation is related to the energy and momentum and the angular frequency. And this relation give the this is the p and E is equal to pc, where p is the momentum of the photon and c the speed of light. Angular frequency is related to the speed of light with the wave vector k. And when we solve it, then we get the relation between the momentum and the wave vector k. Then what is the energy of the photon? As given by the Max Planck, its energy of the photon is quantized, which is given by h mu, which is the mu is the frequency, and h value is the 6.626 into 10 to power minus 34 joule second. And this since they have photon has different mode, different frequency, and according to their mode and frequency, their energy is also different. Since it depends on the frequency, so that the energy can be vary according to their mode. We know that in electromagnetic field there is a polarization. But what about the photon? Photon is when we treat it as a particle, as well as wave also. Then then when we perform the experiment, then we get that the photon has also the polarization property. It's since it has also electric and magnetic property. That's why when it travel to any medium, then it can change their direction of the field. We see that this one is the linear polarization, in which there are inclined to some axis, and this is the right circular polarization, just rotate in the clockwise direction. Another experiment uh, uh, with the photon, the young double pinhole experiment. It showed that the photon also behave as a light, and so the interference property. The one of the major achievement is that it can show the interference with a single photon. When we experiment with the single photon, it show the same intensity distribution is a bright and dark spot. We see, and this is the intensity distribution with which is related to the input of the photon intensity. When we just pass it through the linear operation, then we get the intensity distribution, and this is also informed intensity distribution. Now, another is which is important is how photon interact with matter. When the photon interact with the matter, then there are two types of main interaction. Of course, it's absorption and the emission. Some other effect also like scattering uh, uh, is also happen, but we just don't focus on the scattering. We just focus on the absorption and emission. We see that any photon stack with the atom. If the atom absorbs the energy and just go to the excited state, then it is called absorption. For absorption, it is necessary that the frequency of the photon must match with the electric energy difference between the energy level. Otherwise, it just passes through the material. It don't, or it can't absorb that energy. Now, the spontaneous emission, in which the excited state electron just come out to the ground state with the emitted of photon. It's emit the photon when its electron come to the ground state. There is no external factor. That's why we call it spontaneous emission. Third one is the stimulated emission, which is just electron come out to the ground state with the help of some external factor, or it may be is external factor, maybe a photon or some other factor. We see that when electrons come in stack, it has stimulated the electron and it's come to the ground state with the same polarization, same phase. What is the have the is the external factor or some external photon. Now we discuss about the laser. Laser is the full form of the laser is large amplification by stimulated emission of radiation. We know that the stimulated emission, it is stimulated by some other factor, external factor, or some other. It may be a photon. Then how it works? We know that there is the but from the optical amplification based on the stimulated emission. Let us we amplify it through the stimulated emission. How we see through this figure? First, we just absorb the photon, and the electron get excited. And after when excited, it's come to the ground state. It's emit photon, and this photon is used for the stimulate the other photon, other electron, and it's in the number of photon is increasing as we just with the time it's increasing, and it's amplify the radiation, and after from this amplification we get the laser. We see there are some component which is essential of the laser. First is the gain medium, second is the laser pumping energy, third is the high rate reflected, fourth is the output coupler, and fifth is the laser beam. We see all the component in this figure. In these two sides, there is a high reflective mirror. Approximate one side is 100% and one side is 99.99%. This is the gain medium in which the electron get excited, and the pumping in energy given by the some external source. It can be in the form of light, electron, voltage, electric field, or the in thermal form. We just use the energy to just get the excited state of in the material, and after that, it's when it cross to some intensity, then it's come out from the mirror as in the form of laser. In this figure, there are mostly two types of laser, which is called three-stage pumping or four-stage pumping. In three-stage pumping, first we just excited the electron to higher state, which is very highly unstable. Then after that, it's come to some intermediate state where the relaxation timing is some greater than the higher energy state, which is the non-radiative state. When the electron come to the meta-stable state, there is no radiation. After that, the electron come to the ground state with emitting photon or laser. In the fourth pumping state, when we just pump the energy into the higher energy level, then it's relaxed to the some intermediate state, and this intermediate state is radiate the laser and just come to the some the other intermediate state, and after that it's fastly come to the ground state. There are three stages, that's why we call it three pumping stage, and there are the four step, that's why we call it four pumping stage. Here we discuss about the Ruby laser. Since it's the first laser which was developed, we see the in pumping source there is the flash light, and the as a gain medium it's is the chromium doped material, in which the chromium ion as a gain material. We see the construction of the laser. In this one, the Ruby laser is a three-stage pumping, three-stage pumping laser, in which there are three steps. First is with the green light in 5,500 angstrom wavelength to just excited the electron, then come to a meta-stable state, and then it's emit the red light, which is the just 6.94 nanometer wavelength. We see how its amplification occur when one photon is amplified, the other is another, just do the amplification of the chromium ion atom. Now we see the some optoelectronic device, because when photonics we deal with the semiconductor or the metal-based optoelectronic device, which is a combination of the both optics and electronics. There are two metal, is silicon and germanium, which is preferred in the we preferred in the optoelectronic device, and they work on the two theory. First is the just when the photon interact with the material. The first is the electron hole pair generation by absorbing photon, just to create the electron in the higher state. And the second is the electron hole pair combination. When we go to excited state, then again come to the ground state and combine it. This is the energy state of the material. There is a valence band, and there is an energy gap, and this is the conduction band. When energy a photon stack with it, the material, then some electron go to the conduction band, and the whole there is some generation of hole, and there is some electron which is just combine it and they create the whole electron pair. Now then the how current is flow when the we see that when the photon stack, then the electron goes to the conduction band, and when we add it into some, when we just bias it, then some electric field generated, and that can be allowed to electron to flow through it, and that's why it's just generate the current. And which this is the reverse of this process. When the electron come to the ground state, then it's emit the photon in terms of light. Is the light emitting diode, how it's work? It's just a semiconductor material. Its work as a is similar to the PN junction, and which LED work always in the forward bias. LED is also suitable for the analog modulation, and it's not for the digital. How it works when we do just forward bias, then it's we know that in the forward bias, the potential barrier of the PN junction reduce, so that it can easily combine with the electron and hole. We see that when the uh, photon stack with at the deflection region, then there are some electron hole pair generated because the some electron get the excited, and during the follow bias, they try to move each other in their electric direction. But before reaching to their p or n state, in the deflection region, they just come down to the ground state. For the fabrication, it is necessary then the length of the movement of PN deflection width must be higher than the what is the recombination time of the electron, so that it can combine. Otherwise, when it reaches to the pin or inside or just cross the deflection region, then its light cannot be emitted. Photodetector is a photodetector is a device, especially its main work is to just take the input as a light and give the output as a current. It can be a PN junction or PIN. IN is the intrinsic or the insulated material between the P or N junction. In some photodetector, we can also use the metal, in which we use the Schottky contact. Schottky contact is especially work when we combine the semiconductor with the metal. There are how we define the photodetector. How is depend on the two thing: efficiency and the responsivity. Efficiency is how electron or hole collected in terms of incident photon, means how photon just incident on the material, and how much electron is generated. This is the ratio of the electron to photon, which is called efficiency. And one is the responsibility, which is denoted in the term of power. How intense photon flux just interact with the material, and what current it's generated. This is unit ampere per watt. This is the circuit of the photo detector. And one thing is the photo detector always is a reverse bias. When the light strike with the detector, then we create the electron, and the electron start to flow. One of the electronic device is the optical modulator, in which we just change the intensity, phase, wavelength, and the polarization of light wave. There are different types of modulation, like electro-optics modulation, acoustic modulation, magneto-optics modulation. It depends on the what types of we use for the what factor we use for the modulate the optics. We see that the different types of value we can change in the optics. It's amplitude, phase, and polarization, wavelength. Time is related to when we generate the time delay. It's just create the phase, just change the phase. Position. When we change the position, it's related the phase as well the magnitude. We see in this figure that how the so the relative figure of the modulation. Suppose first one is the undisturbed light, then how the wave show when we change it, like amplitude when we change, then so this type of curve. When we change the phase, this the C, and we change the amplitude and phase both, then we get the profile similar to D. Now let's be just briefly discuss about the some modulator. First is the acoustic optic modulator, in which we use the sound wave to modulate the light. When we induce the sound wave, then it creates some compression and reflection in the material, which is the come in the form of the high refractive and the low refractive. In compression, there is a high refractive index, and the reflection there is a low refractive index. Then we exchange the propagation of light, since when the propagation light is different in high and the low refractive index, then we get this type of profile. In second is electro-optic module material, in which we apply the electric field on the material. Since light is also electromagnetic material, when interact with the electric field, it's change their polarization. Third is the mesh center intensity modulator, in which we use the thermal heat to just modulate the light, just to create the phase difference. When we apply the heat, the refractive index change, and that's why there are the phase gradient generated. Yeah, the last one is the non-linear quantum optics. In non-linear quantum, in linear optics, when we create with when the material passes through any when the light passes through any material, then when the wavelength or frequency is unchanged, then it's a linear one. But when the intensity or through wavelength change, then it is a non-linear optics. Non-linear optics to interact what is the deal with the high intensity light, while the linear optics is deal with the low intensity light. We see that what is the difference between linear and non-linear. In linear, there is a polarization is that linear related to the electric field, but in non-linear optics, it is a non-linearly related to the electric field, double order or triple order, or maybe higher order. It's the when there is absorbed energy, then it emit the same wavelength. But when in non-linear, it's absorb different wavelength and emit the different wavelength optics. The non-linear optics, it can be used for the second harmonic generation, third harmonic generation. It's also used for the 3 or 4 wave mixing, in which we can just generate the entanglement. We don't go too much deep due to the time constraint. Just now this is the last slide. Now we as we said, it is a part of coursework, Introduction to Photonics, which is the course code is 885500, and the course instructor is Dr. Swananju sir, which is assistant professor in electrical department. Thank you.